Hello and welcome to today's session. So today we are going to discuss on another application of Opamp, so that is non-inverting amplifier circuit. So in the previous tutorial we have seen the analysis of inverting amplifier circuit and with its few examples. So now let us look into the circuit of the non-inverting amplifier. So non-inverting amplifier circuit looks similar to the inverting amplifier circuit. So only difference is that rather than the input voltage Vs connecting at a resistor Rs or R1, it is connected to a non-inverting terminal, that is across V2. So now clear this. So if we look into the analysis of this, so it starts with the equation, that is V0 is equal to AV of V2 minus V1. So this voltage at V1 is also called as VF, the feedback voltage. So if we look into the virtual ground concept reality, in the inverting amplifier case, what happened there, the V2, that is nothing but the inverting terminal, was grounded. So due to which and also due to the high input resistance across the input, there was no current flowing through V1. That is why, as V2 was 0 in the inverting case, which was approximately equal to V1, so V1 was also equal to 0. But here the case is slightly different. So here what happens is that, so here V2 is equal to Vs because V0 by AV is equal to 0. So here the V1 voltage is not straight away connected to ground, it is connected through a resistor R1. It means there is some voltage which is coming across here. So the voltage, to analyze the voltage across the V1, it looks like a voltage divider circuit. So if you look like this, so if we connect like this, so this is R1, this is RF, so this is our V out point and this is our V1 point. So this exactly looks like an voltage divider circuit. So we can apply voltage divider formula to find the voltage across V1. So V1 is also equal to Vf, the feedback voltage. So this is given as, so this is equal to R1 into V0 divided by R1 plus R2. We are applying the voltage divider equation here. So we'll get V1 as this. Now if we substitute this equation in this equation 1, so then we will get the V0 is equal to AV of, so V2 is nothing but Vs in this case, so Vs minus R1 into V0 divided by R1 plus RF. So when we simplify this circuit, so let us simplify this circuit, let us simplify this equation. So this is given as page 28. Let me come to new page. So when we cross multiply here, we will get this as, this is AV into Vs of R1 plus RF minus R1 into V0 into AV whole divided by, it is R1 plus RF. So now if we separate these terms, then AV into Vs into R1 by R1 plus RF plus AV into Vs into RF by R1 plus RF minus AV into V0. Just hold on, let us not separate these terms, sorry for that. So let us cross multiply these terms rather than that. So we will have R1 into V0 plus RF into V0 equals AV into Vs of R1 plus RF minus R1 into V0 into AV. Then let us take the terms of V0 on the left hand side. Then we have V0 into R1. So I'll straight away write this by taking these terms, which are the terms on the left hand side. V0 turn to the right hand side to the left hand side. Then we will have a V0 as a common. So then we will have this R1 plus RF plus we have R1 from this term. We have R1 into AV equals we have AV into Vs of R1 plus RF. So then our V0 equation is equal to AV into Vs of R1 plus RF divide by it is R1 plus RF plus R1 into AV. So let us take some assumption here. So ideally we know that the open loop voltage gain is very high when it is and if it is multiplied with R1, definitely it is very much greater than R1 plus RF. So then RV into R1 is very much greater than R1 plus RF. So finally this equation, if we can write here, so let me write here, there is no place, I'll write at this point, I'll move these terms, okay, then I'll write it here. So therefore I'll get V0 is equal to AV of R1 plus RF into Vs. So still we have not applied this point. So in the denominator R1 plus RF is no much of significance when we compare with RV into R1. So in the denominator we have the term RV into R1. So now let us cancel these terms, that is RV into these terms. So let me move these equations. So then finally I am left out with, when I cancel this, so we have V0 is equal to, so if I divide this term, I can write this as 1 plus RF by R1 into Vs. So this is the equation, the final equation for a non-inverting amplifier. So this 1 plus RF by R1 defines the closed loop gain, that is AF. So this defines the closed loop gain for non-inverting amplifier. So let us revise this equation. So this equation is nothing but V0 is equal to 1 plus RF by R1 of Vs. So this we got by considering the case where AV into R1 is very much greater than R1 plus RF. So then we have come to this point. So here also we can note that the output voltage does not depend on open loop gain, it depends on the closed loop gain, that is AF. Now let us see one simple example. Let me save this page, page 29. Okay, so let us take the circuit. Yes, an voltage source is connected here. So this voltage source is nothing but it is Vs is equal to 1 milliamp output, and this is grounded here, so this is my R1 and this is RF. So this is of 10 kilo ohms, and this is 100 kilo ohms. This is V0. So we have to determine the closed loop gain and output voltage. So we have to find the AF, what is AF, and we have to find what is the output voltage. So let us take the non-inverting amplifier equation. So that is given by V0 is equal to 1 plus RF by R1 into Vs. So straight away we can substitute all the values in this equation. Then finally we will get this voltage, the output voltage, as 11 millivolts, and AF is nothing but it is 1 plus RF by R1. We can substitute the values in this equation, then we will get this is equal to 11. Simple analysis, isn't it? Now let us look into a cascade section, a very interesting example here. Let me save this as page 30. A very interesting example, a cascade example. So this Vs here, this is equal to 10 millivolts, and this is grounded. So here we have the feedback network. So this is of 10 kilo ohms, and this is 1 kilo ohm. So this is inverting, this is non-inverting. So now we have one more Opamp here, so where this is 2.2 kilo ohms, this is 1 kilo ohm, where it is connected to inverting terminal, whereas the non-inverting terminal is grounded. Very, very interesting example. So final output we have to find. What is the final output? So if you look at this example, so this is a non-inverting case, whereas this is an inverting amplifier case. So let me write this here. So this is a non-inverting amplifier, and whereas this is an inverting amplifier. So how to solve this example? So we have to treat this part by part. So first we will analyze this this circuit, then whatever the output we will get, so that will act as Vs for this circuit. So for this I'll call this as the intermediate output voltage VO1. So where VO1 is equal to Vs1 in this intermediate input for the second circuit. So then we can apply the equation of inverting amplifier, and then we can analyze this. So now let us quickly jump on to the equation. So in this first case, let us find VO1. We have to use the different notations, please understand, because we are finding the intermediate output. We are not finding the final output, so please do not write it as V0. So let us write as a separate term, that is as VO1. So VO1, we know that it is a non-inverting amplifier, so the equation is 1 plus RF by R1 into Vs. So straight away you can apply here. So my RF is 10 kilo ohms, so it is 1 plus 10 kilo ohms by 1 kilo ohm, and my Vs here it is 10 milliamperes, 10 millivolts applied. So we will get here the 10. So here my AF1 is 11. So there are different methods to analyze this. So it is I'll get this as 110 millivolts. So I'll get this as 110 millivolts. Now let us apply this to this. I'm talking about this one method. So there is another method of analysis that we will talk about later. So V naught is here, it is equal to minus RF by R1 into Vs1. So now in this case the RF is corresponds to the second circuit and R1 corresponds to this circuit, that is here. So now it is minus 2.2 kilo ohms divided by 1 kilo ohm into this is 110 millivolts. So when you finally calculate this, so you will get this as finally minus 242 millivolts. Hope the calculation is correct, intermediate calculations and everything. Yeah, this is one method of analysis. Final output voltage across this point we are getting a minus 243 millivolts. We applied, say this, there are two stages of amplification. Whether it is positive amplification or negative, means inverting or non-inverting, you need not to bother, but there are two stages of amplification. The first stage of amplification we got an output of 110 millivolts, and second stage of amplification we got a minus 242 volts, 242 millivolts. Okay, so this minus again represents because here in the final stage we have given the input to a inverting case, so the output is inverted by 180 degree. That is the meaning of it. Okay, other than that there is nothing else. So this is one method of analysis. So if I talk about the second method of analysis, then I'll have to clear this. So if I clear this, then so second method of analysis is we'll calculate the closed loop gain for this first circuit and the closed loop gain for the second circuit, and then we will multiply both the gains, and then we will multiply that with the final input. So that is another method. So let us do that. So AF1 is equal to, we know that it is 1 plus RF by R1. You calculate AF1 is with respect to this circuit, so this is AF1. So this we got it as 11, and here the AF2 is nothing but minus RF by R1. So from this circuit, so we'll get this as AF2, substitute this RF and this R1 value here, so we will get this as minus 2.2. So now calculate the final AF. So final AF is equal to AF1 into AF2, so that we will get this as minus 24.2. So then finally the V0 is equal to AF into Vs, so this is equal to minus 24.2 into 10 millivolts, which we will get it as minus 242 millivolts. Okay, so this is another method of analysis. We can follow any of the method, whichever is convenient, so please follow that. So I prefer with the first method is convenient, because as there is more number of cascade sections, it is always better to first finish off section by section, then you can compute to the final output. So thank you for watching this tutorial. So in the next tutorial we are going to talk about the more applications of Opamp, so probably the adder and subtractor circuits. Thank you.